Hello there, CFA candidates. Today we're going to dive into the nitty-gritty of statistical measures of asset returns. Understanding these concepts is super important for your CFA Level 1 exam and your future career in investment analysis and management. So, let's get the ball rolling. Data is the bread and butter of investment analysis and management. However, the real challenge is turning this data into useful information, are essential for investment pros like yourselves. This module sets the stage for understanding key concepts in data analysis that, in the investment world, data helps you make informed decisions. Whether you're analyzing stock performance, evaluating portfolio returns, or assessing market risks, data is your foundation. For instance, knowing the historical returns of a stock can help you predict its future performance. However, raw data alone isn't enough. You need to process and analyze it to extract meaningful insights. That's where statistical measures come into play. All right, let's talk about measures of central tendency. These measures help us figure out the middle ground of a data set. The most commonly used measures are arithmetic mean, the sum of all observations divided by the number of observations. Median, the middle value in a sorted list of observations. Mode, the most frequently occurring value in a data set. Weighted mean, the mean where different observations have different weights. Geometric mean, handy for computing the mean value over time. Harmonic mean, great for averaging ratios. Let's start with the arithmetic mean. This is calculated by adding up all the observations and dividing by the number of observations. It's often just called the mean or average. For a sample, the formula is this. So you take each observation, add them up, and then divide by the total number of observations. Simple enough, right? Now, a couple of things to remember about the arithmetic mean. Number one, the sum of deviations around the mean is always 0. Number two is about sensitivity to extreme values. The arithmetic mean can get thrown off by outliers, which are those really high or low values. Speaking of outliers, these are extreme values that can mess with your data. There are 3 ways to handle outliers. Number one is do nothing, just roll with all the data as it is. Second is delete outliers. Calculate a trimmed mean by chopping off a small percentage of the lowest and highest values. Third is replace outliers. Calculate a Windsorized mean by replacing extreme values with specified values. Let's say we have the monthly returns of a stock over 6 months. 3%, 5%, minus 2%, 7%, 0%, and 4%. The arithmetic mean return is approximately 2.83%. Notice how the minus 2% impacts the mean, demonstrating the sensitivity to outliers. Next up is the median. This is the middle value in an ordered list of observations. If the number of observations is odd, the median is the center observation. If it's even, it's the average of the 2 center observations. The median isn't phased by outliers, making it a solid measure of central tendency. Now, let's chat about the mode. This is the value that pops up the most in a data set. Distributions can be unimodal, 1 mode, bimodal, 2 modes, trimodal, 3 modes. All right, everyone, let's jump right into the weighted mean. This is a super useful concept, especially when you want to give different importance to different observations in your data set. It's like saying, hey, not all data points are created equal. Imagine you're evaluating the performance of a portfolio consisting of different stocks. Not all stocks are equally represented in the portfolio. Some have more weight, more invested in them than others. In this scenario, using a simple average wouldn't give you an accurate picture of the portfolio's performance. You need the weighted mean to get a true sense of how the portfolio is doing. Let's go through a quick example. Suppose you have a portfolio with two stocks. Stock A has a return of 8% with a weight of 70%. Stock B has a return of 4% and a weight of 30%. To calculate the weighted mean return of the portfolio, you'd use this formula. So the weighted mean return of your portfolio is 6.8%. Let's say you're an analyst looking at the performance of different sectors within an index. You'd want to use the weighted mean to ensure that sectors with larger market caps, more weight, have a bigger impact on your analysis compared to smaller sectors. The geometric mean is great for calculating average growth rates, especially when you're dealing with investment returns over multiple periods. The geometric mean is particularly useful in finance because it gives a more realistic measure of an investment's performance over time. If you're looking at a series of returns, the geometric mean will always be less than or equal to the arithmetic mean because it smooths out the volatility over multiple periods. The harmonic mean is a bit different from the arithmetic and geometric means, and it's particularly handy when you're dealing with rates or ratios. Imagine you're averaging speeds or prices per unit. That's where the harmonic mean shines. Instead of just adding up the numbers and dividing, the harmonic mean takes the reciprocal of each number, finds their average, and then takes the reciprocal of that result. This method gives more weight to smaller numbers, making it great for situations where you want to balance out extreme values. For example, if you're looking at cost averaging in investments, where you invest a fixed amount regularly, the harmonic mean will give you a more accurate picture of your average price paid. It's like having a tool that helps you see the forest despite all the tall trees. It smooths out the big variations and gives you a clear view of the typical scenario. Quantiles are values at or below which a certain percentage of data falls. They include quartile, quintiles, deciles, and percentiles. Quartiles divide data into 4 parts. Quintiles divide data into 5 parts. Deciles divide data into 10 parts. Percentiles divide data into 100 parts. All right, now let's move on to measures of dispersion. These measures give us the lowdown on how spread out the data values are. These are the types of dispersion. Range is the difference between the maximum and minimum values. Mean absolute deviation is the average of the absolute deviations from the mean. Variance is the average of squared deviations from the mean. Standard deviation is the square root of the variance, making it easier to interpret because it's in the same units as the data. All right, let's talk about downside deviation and coefficient of variation. These measures are crucial for understanding the risk and variability in your data, especially from an investment perspective. Downside deviation is a risk measure that focuses on returns that fall below a minimum threshold or minimum acceptable return. Unlike standard deviation, which considers all deviations from the mean, downside deviation only looks at the negative deviations. This is particularly useful for investors because it emphasizes the downside risk, the part we're all most worried about. Let's go through an example to make this clearer. Suppose we have stock returns for 5 periods. These are the values. We'll set our target return at 10%. First, we identify the periods where returns are below the target. This means all returns below 10%. These are 9.3%, minus 11.1%, and minus 17.0% in our example. Next, we calculate the squared deviations from the target for these returns. Sum these squared deviations, then divide by the number of observations minus 1. So our downside deviation is approximately 17.14%. Now, let's move on to the coefficient of variation, abbreviated as CV. This measures relative dispersion and is calculated as 100%. This measure tells us about the relative dispersion in our data. It's the ratio of the standard deviation to the mean and is particularly useful because it's scale independent. This means you can use it to compare the variability of data sets with different units or vastly different means. This is the formula for coefficient of variation. A higher CV indicates greater relative dispersion around the mean. In investment terms, a higher CV means more risk per unit of return. Comparing CVs across different assets can help you understand which investment has more relative risk. To summarize, downside deviation helps you focus on the potential for losses, while the coefficient of variation gives you a standardized measure of risk relative to the mean. Now, let's talk about measures of shape of a distribution. This tells us about the symmetry and peakedness of the distribution. Let's talk about skewness. This is a measure that tells us about the asymmetry of the distribution of data. Skewness indicates whether the data points are symmetrically distributed around the mean or if they are skewed to one side. In simpler terms, it tells us if the data leans more towards the higher or lower values. To get a better grasp of this, we'll refer to some diagrams that illustrate various distributions. There are three different types. First is symmetrical distribution. In a perfectly symmetrical distribution, the mean, median, and mode are all the same. This is often referred to as a normal distribution. In our diagram, this distribution will have a perfectly balanced shape with no leaning to either side. This diagram shows a bell-shaped curve that is perfectly balanced on both sides. The mean, median, and mode are all located at the center of the distribution. Now, let's look at the positively skewed or right-skewed distribution. This distribution has a longer tail on the right side. This means there are more lower values and fewer higher values. In a positively skewed distribution, the mean is greater than the median, which is greater than the mode. In the diagram, you will see the peak shifted to the left, with a long tail extending to the right. This indicates that most of the data points are clustered around the lower values, with a few extreme higher values stretching the tail out to the right. Third is negatively skewed or left-skewed distribution. This distribution has a longer tail on the left side. This means there are more higher values and fewer lower values. In a negatively skewed distribution, the mean is less than the median, which is less than the mode. In the diagram, you will see the peak shifted to the right with a long tail extending to the left. This indicates that most of the data points are clustered around the higher values, with a few extreme lower values stretching the tail out to the left. Understanding skewness is important because it gives us insight into the direction and magnitude of deviations from the mean. For investors, skewness helps assess the likelihood of extreme returns. A positively skewed distribution might indicate potential for high returns, but also more volatility. A negatively skewed distribution might indicate more consistent returns, but a higher chance of significant losses. All right, let's dive into kurtosis. This is an important measure to understand the shape of a distribution, specifically how peaked or flat it is compared to a normal distribution. To get a better grip of this, we'll refer to some diagrams that illustrate different types of kurtosis. Kurtosis helps us identify the tailedness of the probability distribution of a real valued random variable. In simpler terms, it tells us whether the data have heavy tails or light tails compared to a normal distribution. There are three types of kurtosis. Number one is leptokurtic. This distribution is more peaked than the normal distribution. It has fatter tails, meaning there's a higher probability of extreme values. Picture a tall, skinny peak with long tails. This indicates more frequent extreme deviations from the mean. In this diagram, the leptokurtic distribution is the one with the sharp peak and long tails. Second is platykurtic. This distribution is flatter than the normal distribution. It has thinner tails, meaning fewer extreme values. Think of a wide, flat peak with short tails. This indicates less frequent extreme deviations from the mean. In the diagram, the platykurtic distribution looks more spread out and less peaked. Third is mesokurtic. This is your normal distribution. It has a moderate peak and tails, serving as the standard reference. In our diagram, the mesokurtic distribution is the one that sits perfectly in the middle with an average peak and tails. To quantify kurtosis, we use excess kurtosis. The formula is kurtosis minus 3. For a normal distribution, means mesokurtic, the excess kurtosis is 0. If the kurtosis is greater than 0, we have a leptokurtic distribution. And if it's less than 0, we have a platykurtic distribution. Now, let's look at the diagram. The leptokurtic distribution shows a sharp peak with long tails. It indicates a high level of kurtosis, suggesting more data points are close to the mean with significant outliers. The mesokurtic distribution is the normal distribution. The peak and tails are moderate, representing no excess kurtosis. It's our benchmark for comparison. Now look at the platykurtic distribution. This shows a flatter peak with short tails. It indicates low kurtosis, suggesting data points are spread out more evenly and less clustered around the mean. Understanding kurtosis is crucial because it helps us understand the risk of extreme values. For investors, a leptokurtic distribution might mean higher risk due to the potential for extreme returns, both positive and negative, while a platykurtic distribution might suggest more stability and less risk of extreme outcomes. All right, class, let's dive into the final topic of this session that often trips people up: correlation and covariance. It's important not to confuse these two, even though they are related. Correlation measures the linear relationship between two variables. It is all about understanding how two variables move in relation to each other. Are they best buddies that move together? Or are they like oil and water, always going in opposite directions? So correlation gives us a number that tells us how strong the relationship is between two variables. This number, called the correlation coefficient, and denoted by R, that can range from -1 to +1. +1 means perfect positive correlation. Imagine they're best friends who do everything together. If one goes up, the other goes up too. -1, on the other hand, means perfect negative correlation. These are frenemies. If one goes up, the other goes down. 0 means no correlation. These guys don't care about each other at all. One moves, the other might do anything. Here is the formula for correlation. It is the covariance of x and y divided by the product of their standard deviations. This standardization makes correlation a dimensionless measure, allowing us to compare relationships between different pairs of variables. Understanding correlation is key because it helps you figure out the strength and direction of relationships between variables. In finance, this can help you determine how different assets move relative to each other. Imagine you're looking at two stocks. If you find a high positive correlation between their returns, it means they tend to move in the same direction. This info is gold for building a portfolio. For diversification, you'd want to mix in assets that don't move together, or even better, have negative correlations to spread out the risk. Another related concept is covariance. Covariance measures the direction of the linear relationship between two variables. If the variables tend to increase together, the covariance is positive. If one variable tends to increase when the other decreases, the covariance is negative. Here is the formula for covariance. X and y are the variables x bar, and y bar are their mean values. To calculate covariance, we'll first calculate the mean of x and y, then subtract the mean from each data point to get the deviations. Now, multiply the deviations of x and y for each data point. Sum these products and divide by the number of data points minus 1. This process gives us the covariance between x and y. It's important not to confuse correlation with covariance, even though they are related. They are different from each other in terms of scale, magnitude, and interpretation. How? Let's explore further. Covariance is measured in units that are the product of the units of the two variables, making it difficult to interpret directly. Correlation, however, is a dimensionless number ranging from -1 to +1, making it easier to understand and compare. Covariance values depend on the scale of the variables. Larger values don't necessarily mean a stronger relationship, but could simply result from larger numbers in the data. Correlation normalizes this by dividing by the standard deviations, giving a consistent measure of relationship strength regardless of scale. Correlation provides clear insight into the strength and direction of a relationship, whereas covariance only indicates the direction. Okay, now let's wrap up with the limitations of correlation analysis. There are 5 key points you need to remember. Number 1 is linearity. Correlation only measures linear relationships properly. So if there's a nonlinear relationship between the variables, correlation might not pick it up correctly. Number 2, outliers. Outliers can really mess up the results. Just one extreme value can distort the correlation and give you a misleading sense of the relationship between the variables. No proof of causation. Remember, correlation doesn't mean causation. Just because 2 variables move together doesn't mean one causes the other. There could be other factors at play. 4th point is spurious correlations. Sometimes you'll see correlations that are just plain fake. These spurious correlations don't mean anything and can happen purely by chance or due to a third variable influencing both. Lastly, incomplete story. Correlation doesn't give you the whole picture. It tells you about the direction and strength of a linear relationship, but nothing about the underlying dynamics or other important details of the relationship. So keep these limitations in mind when you're analyzing data, and always dig deeper to understand the full story. Suppose we find a high correlation between ice cream sales and shark attacks. This doesn't mean buying ice cream causes shark attacks. There's likely a third variable, like warm weather, causing both. By mastering these concepts, I mean really getting them down cold, you'll be so much better equipped to make informed investment decisions. You'll be able to assess risk, evaluate portfolio diversification, and even spot potential opportunities that others might miss. So here's my advice. Practice. Practice these calculations. Review those examples in your CFA curriculum. Really get your hands dirty with the data. The more you work with these concepts, the more intuitive they'll become. Thank you for sticking with me. I hope this lecture helps you get a grip on the essential statistical measures of asset returns. Keep at it, and you'll ace that CFA Level 1 exam.